Okay, we're underway. I'll share my screen. So I've issued these notes. Hopefully you've all received them, whether you've had a chance to look at them or not. So we're going to talk a bit more about chillers, water chillers, sometimes called refrigeration machines. And we'll probably have another session on this later on about selection of chillers in more detail, but it's really just raising more awareness about chillers and things to look out for and what's available. So in stage 2, we looked briefly at chillers as a source of cooling for air conditioning or process temperature control. In this session, we'll look more closely at chillers and the typical controls for them. There's all sorts of controls. You can make it as complex as you like or try and keep it simple. I've always tried to keep control systems simple so that you don't get doesn't get too difficult to manage. Depending on how many chillers you have and what sort of system it is, you've got to design the control system to suit that. We'll also have a look at some typical pipe work configurations. And I'll give you a little bit of history as we get into that. So water chillers can be water-cooled or air-cooled. Water-cooled means that the chiller has a water-cooled condenser, and air-cooled chillers have an air-cooled condenser similar to a DX air-cooled condenser. So I'll show you a picture. We've seen this one before in the previous session. That's a water-cooled chiller. It's got a water-cooled condenser vessel, evaporator vessel, and the condenser water is connected. These pipes take it off to a cooling tower or fluid cooler, more likely a cooling tower, to reject the heat from the system. Air-cooled chiller is it's got the air-cooled condenser with fans on the top, and this is the evaporator vessel at the bottom and compressor under there. Water-cooled chillers have greater energy efficiency than air-cooled because of the lower temperature of condenser water compared with ambient air. So condenser water is typically, let's say, around 30 degrees coming back to the chiller, or 29 to 30 degrees, compared with ambient air, which may be 40 degrees or higher. And water has a higher thermal conductivity than air anyway, so it makes a much more efficient chiller. But they're more expensive. They're more compact. You can get a lot more capacity out of a water-cooled chiller than you can out of an air-cooled. So air-cooled varying capacity from very low up to around 1,500 kilowatts. They keep increasing these things all the time, so you can probably find something a bit higher than that if you need it, but they get very large. Typically, per 100 kilowatts, you're talking about a metre in length. So that's a rough rule of thumb that might stick in your head if you're thinking about how big they might be. 1,500 kilowatts is probably 15 metres long. It's huge. And it takes a lot of space. It's got to be outside on a roof or on the ground outside. Water chillers can go from very low capacities, but can range up to about 10,000 kilowatts. And I was just doing a bit of research this morning, and I found a new oil-free magnetic bearing compressor that goes up over 12,600 kilowatts. So that's with multiple compressors. I'll show you a picture of that in a minute when we get down to that. Water-cooled chillers are generally used in large projects to provide the cooling capacity required and the best energy efficiency. Traditionally, an air conditioning system using water as the so-called refrigerant or heat source would include a chiller for cooling and hot water heaters or boilers for heating. In the next session, we're going to talk about boilers, heaters, water boilers a bit more, and their control systems and configurations. In recent years, there's been many developments in chillers to provide flexibility and better energy efficiency. Heat pump chillers. These chillers can provide cooling or heating by reverse cycle operation. They're two-pipe chillers, which means the they're either doing cooling or heating. You can't do the same thing at the one time. So you've got to change over. You've got to have a changeover valves and pipe work to deliver cooling or heating. These chillers are suited best to summer or winter operation. If simultaneous heating and cooling is required, then multiple chillers are necessary, or an alternative heat source like water is required. Multi-function chillers, I'll highlight that, or 4-pipe chillers. These chillers can provide cooling and or heating simultaneously, so that one machine can give you both. It's got 4 pipes. You've got a cooling side and a heating side. You can have full cooling, full heating, or somewhere in between where you get some cooling and some heating, depending on what you need in the system. The heat that's normally rejected to the atmosphere in the cooling mode is available for heat recovery, simultaneous use in the heating system. So they give you good, very energy efficiency. They'll probably, if you compare chillers, they'll give you the best energy efficiency that you can get. But they're not suitable to all projects. And they're limited in capacity. They probably go up to about 1,000 kilowatts, but you can research that. All this stuff that I'm talking about, you can find a wealth of information online. If you want to go and have a look at chillers, knock yourself out. You can look all day at chillers. There's a lot of information available. 4-pipe chillers are best suited for use in commercial buildings that require simultaneous cooling and heating in different parts of a building for a significant portion of the year. So in other words, in times of neither extreme heat or cold. I think Woolworths, if you do a Woolies job, they have their standard brief on what they require in their projects, and I'm pretty sure one of the requirements now is for multi-function chillers, so that they can have cooling and heating simultaneously. Coles and Woolworths they have their own engineering teams, and they're very switched on to energy efficiency. So if you're doing one of those, make sure you comply with what they're asking for. Modular heat pump chillers. These chillers comprise multiple small chillers which can be connected together. So a whole bunch of small chillers. You can connect them up into a common pipework system to build up their capacity. Building blocks for chillers. For example, in non-extreme weather, one set of modules could provide cooling while another set of modules provides heating. So I know Hudson's had a similar job like this, where they're all the same chillers, but you might have one group that's doing cooling, one group that's doing heating. But then if you need 100% heating, you can have all the chillers running on heating, or vice versa, all on heating. In between, you can have some doing cooling, some doing heating. Does that make sense? So you can group them. The modules can be put together in groups. So let's say you put 5 in one group, 5 in another group. You've got 50% cooling, 50% heating, or you can have 100% cooling, 100% heating. And in recent years, well, I suppose it's probably been the last 15 years or so, variable speed drives have been quite common for compressors. So this enables the compressor speed to be reduced as the load reduces and provides considerable electrical energy savings. Variable speed drive compressors are generally more expensive than direct drive. Well, they are in 99% of cases. If you're using magnetic bearing chillers, which we'll talk a bit more about shortly, they come with a variable speed drive built into the compressor. So you don't have an option there. You get that. Another development has been variable flow through water chillers. The water chiller manufacturers around the world are responding to the energy efficiency improvements that the world requires. So they've done a lot of development with chillers, and you can have. It used to be that you had to have a constant flow through a chiller, but now you can get variable flow chillers. You can still get constant flow chillers, but variable flow chillers have the control system and safety protection to provide that feature. And reducing the flow through the chiller reduces your pumping power, reduces your compressor power. So it all gives you good energy savings. You can get packaged chillers. They're usually smallish chillers, probably up to about 400 kilowatts, with a hydronic module. So they include pumps and valves and sometimes balancing valves and other things, so that you don't have to have an external pump. It's all built into the chiller, and they can be quite useful. Excuse me. I'll just put a note here that some manufacturers or suppliers keep a selection of chillers in stock in Australia. This is pretty handy sometimes if you've got a quick job and you need a chiller in a hurry. But usually they're only up to about 400 kilowatts, because they're not going to build chillers of 1,000 kilowatts or more and hope that somebody wants to buy it, because it's too expensive for them. But small chillers, they have a big turnover, so they keep some in stock, which is pretty handy. The likes of, well, I know Carrier always have chillers in stock. Geoclima, Smart, probably the others, Train and York, they probably all have chillers. So if you've got a job that comes up and somebody says to you, I need this job done in a real hurry, we need it done before Christmas, let's say, before summer. And it turns out that the capacity is 400 kilowatts or thereabouts, or it might be 800 kilowatts. You might be able to buy two 400 kilowatt chillers. And your clients are very impressed if you say, yes, we can get that done for you. So that's good to know. Where I used to work, we kept a list. We kept updating lists from manufacturers or suppliers about what was available. So we could have a quick look and say, yes, there is one, or there was one available. Check it out, get the job done. The different types of compressors, we did mention this previously, but I'll just run through it again. Centrifugal, they can be direct drive or variable speed drive. So looking back at that first slide, well, it's pretty hard to see, but there's a centrifugal compressor sitting up there on top of the chiller. Magnetic bearing type, they're oil-free. It's worth having a read on magnetic bearing chillers, because these are the most energy efficient chillers available on the market. And the combinations that they use on the chillers can provide really good energy efficiency. They have an integral variable speed drive, and as I mentioned, well, I'll show you a slide of these. This is just something I had a look at this morning. V-class water-cooled chiller. Can you still see that? Just nod your head. Okay, so this one, now the last time when I was working on a project about 4 or 5 years ago, we looked at a chiller which was about 7,000 kilowatts. And at that time, I think it had 10 compressors. So 10 compressors of 700 kilowatts each in this sort of arrangement, where you've got multiple magnetic bearing chillers sitting on top of a couple of vessels. Well, I was interested to see this morning, I don't know how long this has been around, but you can now get up to 12,660 kilowatts, and I'm assuming that is 12 compressors of 300 tons each, or about 1,000 kilowatts each. So they're just developing all the time. Various refrigerants are available. So as new refrigerants come on board, they try to make them work in these compressors. So pretty exciting stuff with chiller development. Now, looking at this picture here, looks like Cindy is joining us. You can see the ends of the vessels here. Morning, Cindy. With the yellow caps on the end, they actually appear to be stainless steel. Okay. Obviously, the caps are where the pipework connects to it. And these are the water boxes on the chiller. So the smaller one is the evaporator, the large one is a condenser. These are just standard water boxes. They're not marine water boxes that we've talked about before. But they're, and the end tube sheet there, they call that the tube sheet, that plate that these boxes are fitted to. That's stainless steel as well. So that's an option that's available with these machines. It does cost more money, but there's always the corrosion issue with condenser water systems that we've talked about before. So that's something to consider as well, to spend a bit more money and reduce your corrosion risk. So other compressors, there's screw type compressors, helical, rotary or screw. You can get them direct drive or variable speed. Scroll compressors are normally just on-off type compressors. So in a 400 kilowatt machine, you might have 4 compressors, you might have 8. And they can be just stepped up as required to increase the capacity. You can also get rotary DC inverter for small chillers, but they're pretty uncommon. So the selection choices between the various chiller options are vast and take into account thermal capacity, energy efficiency, size, location, accessibility, etc., maintenance requirements, and of course the cost. So for the MEPEC people, the engineering checklist gives you a list of things to check when you're looking at chillers, and the chiller checklist when you're reviewing or selecting chillers. That's helpful to see what options are available or the sort of things you need to think about. I'll show you a few more slides just to so you can see the sort of information that's out there. This is from the Carrier website, and this is just a bit of a summary of the chillers that they've got available and the capacity ranges. So water-cooled centrifugal, water-cooled VSD screw chiller, water-cooled screw chiller, air-cooled scroll chiller, modular air-cooled scroll chiller, air-cooled scroll heat pump, modular air-cooled scroll chiller, air-to-water heat pump, etc., etc. So you can find that stuff online and have a look for yourself. This is a blue box 4-pipe multi-function chiller. Okay, these are the ones that can do heating and cooling simultaneously. Quite a few manufacturers produce these now, but I'll just put this one up. So if you wanted to do a bit of research on these, you could look at Blue Box. If you Google Blue Box, you'll find all the information you want, but you'll find other manufacturers as well. Most of these chillers come from Italy. They seem to specialise in this type of chiller. Clima Veneta is another one, which Mitsubishi, Mitsubishi own Clima Veneta now. So there's quite a few options there. Just be careful with these that you read the technical data, because from my recollection, on both the chilled water and the heating water, on the both chilled water and heating water sides, you need buffer tanks, and quite large buffer tanks. So just be aware of that. Don't design a system without that. And there's the smart chiller again. That one's got looks like it's three compressors. Interesting story behind smart chillers. It started off, the designer was based in Melbourne, and these guys were the ex-Carrier people in Melbourne. They designed this chiller. Smart in Germany, I think, bought them out. Don't quote me on all this, but and then the compressors you can maybe see on the compressor there, Danfoss. They're a very big name in refrigeration components. They bought the rights to manufacture the compressors. So most of the magnetic bearing compressors now are made by Danfoss in, I think it's in Sweden. But there are others. York have their own magnetic bearing compressor. Carrier have their own magnetic bearing compressor, and probably Trane do now as well. So lots of options. It's an interesting field, and it's quite a big field. So I'll close some of that down. And talk about buffer tanks. Chiller manufacturers, like that. Chiller manufacturers often require a specified minimum loop water volume to be provided around the chiller to maintain accurate chill water temperature control and ensure that compressors do not cycle unnecessarily. If compressors cycle continuously, compressor failure may occur. So the required loop volume varies for different manufacturers. So if you're looking at a particular chiller, let's say it's a Carrier, you need to find out what Carrier's requirements are for the minimum loop volume. And I'll explain what it is. I'll show you now what I'm talking about. This is just, can you see that little sketch? This is just one of my rough sketches to illustrate the minimum loop. So the highlighted yellow part is the minimum loop in this case. So you've got a chiller, or could be multiple chillers, a pipework that comes out of the chiller towards the field, and a bypass valve. Back through, I've put a buffer tank in there, back to the chiller. That is the minimum loop, because if that bypass valve is open, let's say the field is closing down, all the water will go through the bypass. There's your minimum loop. And if there's not enough water volume in there, the chiller is going to start and stop continuously, which will lead to failure of compressors. And I've seen it happen. And sometimes it's a mystery, but if you provide the buffer tank of the right volume, then you should be okay. And if you don't provide it and you have failures, the chiller manufacturers will say, well, you know, I told you that you needed that. So the warranty might be affected by that if you don't provide it. So as I said there, the minimum loop is the volume of water contained in the closest circuit to the chiller and includes the fluid in the evaporator. So there could be quite a bit of water in the evaporator, which you can take into account. If there's a bypass valve between the flow and return, which is the sketch I just showed, before it branches off to the field, to an air handling unit or fan cool unit, then the minimum loop is the one with the bypass valve. So that's pretty easy to get your head around. If the loop volume is insufficient, so in other words, if your loop around the chiller doesn't reach the requirements of the supplier, one solution might be to increase pipe sizes. That might be the easiest and the cheapest way to do it, if it's practical and economical. So instead of having a, let's say, 100 diameter pipe, you might say, well, why don't we make it 150 diameter if that makes up the volume? Obviously, it's going to cost more for the pipe work, but it might be cheaper than putting a buffer tank in. If you can't achieve that economically, you need a buffer tank to provide at least the shortfall in the required volume. Buffer tanks help to reduce the frequency of a chiller cycling, which is energy intensive and can lead to premature failure of compressors. By providing the reservoir of chilled water, the buffer tank allows the chiller to operate more efficiently by running for longer periods at optimal capacity. The buffer tank also helps to mitigate temperature fluctuations in the distribution system, ensuring a stable and reliable supply of chilled water to the connected loads. I'll show you a picture of a buffer tank. There's one there. That one's been pre-insulated and sheathed. Obviously, the buffer tank has to be insulated and it's got to be pressure rated because it's part of the pipework system. It's like a big pipe, if you like. This one is 5,000 litres. So you need to calculate what volume you need, deduct the volume within that minimum circuit, and then that'll tell you how much extra volume you need. And in most cases, you'll need a buffer tank. It's difficult normally to do it with pipework. It's preferable to locate the buffer tank on the return side of the system on the chiller side of the bypass. So on the upstream of the chiller, the downstream of the bypass. System control and energy efficiency can be further enhanced by installing a buffer tank larger than the minimum required. So you don't have to provide, doesn't have to be exactly the minimum. You can put in a bigger one, and that will give you some storage, some energy savings, but it will cost more. So, and it'll be bigger. So if you've got space and you've got a bit of spare cash in the job, maybe it's better to put a bigger buffer tank in to be safe and to provide better efficiency. So looking back at this little sketch, you can see where I've put the buffer tank there. So the field is out here in the minimum loop, comes through the bypass, through the buffer tank and back to the chiller. So it's on the return side. Different people have different views on this. Some people might say, oh, well, we want the buffer tank on the supply side. You can do that, but in my experience, it's better to have it there, and most manufacturers prefer it at the inlet to the chiller. Okay, now bypass valves. This is always an interesting one. They can be located in various parts, but all chillers have a specified minimum water flow to ensure safe and stable operation. We're going back, I don't know how many years, but let's say 15, 20 years ago, probably even less, 10 to 15. I'd say just about all chillers were based on a fixed flow. So the design flow was the flow through the chiller. You didn't change it, you left it as it was, and you had a bypass to make sure you can maintain that flow. As I said here, in some cases, the minimum flow may be the same as the design flow, and that's still the case for a lot of chillers. You don't vary the flow. In general, the minimum flow will be maybe less than the design flow. When designing a chilled water system, it's necessary to ensure that the water flow in the system doesn't drop below the required minimum flow through the chiller. Otherwise, you'll get into strife. You can cause freeze-ups. This was the original issue, that if the water flow was too low, you can get freezing in the chiller and failure. The minimum water flow will vary for different chiller types and manufacturers. So when you're looking at chillers, just be aware or make sure you know what the minimum flow is. And if you're doing a highly energy efficient job, you probably will have a variable flow chiller. So you'll have to account for that. The flow through the cooling the heating coils is controlled by either two-way or three-way motorized control valves. We've talked about them before. Two-way control valves generally provide better energy efficiency, as the flow to the coil will reduce as the load reduces. So as the load in the space is reducing, temperatures reaching design, you reduce the water flow. When the flow reduces, the system pressure will increase. So your pump is, I'm just going to try and keep this simple because it can get a lot more complicated, but the pump is producing so much water, 100% of flow. It's going through the chiller out to the field, and then the field's control valves start to close down. The pressure increases. But where does the water go? So in order to control the increase in system pressure and flow reduction, the two-way bypass valve is normally installed between the flow and return pipes to modulate towards open to maintain at least the minimum allowable flow through the chiller. Okay, so that's that diagram we looked at before. I'll show you again. So if the field is at 100% load, you've got 100% flow going out. But as the valves start to close, pressure builds up. There's a differential pressure sensor across the flow and return pipes. And the bypass will start to open to return some water directly to the chiller. So you get a mixture of water coming back from the field and mixing with the bypass to go back through the chiller and maintain a constant flow. So the bypass valve responds to a differential pressure sensor or transducer installed between the flow and return pipes. Downstream of the pumps and buffer tanks were installed. Sorry, downstream of the pumps and buffer tanks. Yes, the actual location of the bypass valve is determined to suit the system design, but normally in the chiller plant area. Sizing of bypass valves. This is often debated. If you consider a simple chill water system with one chiller only, morning, Stephen, which operates on design flow at all times. So when the field is at full load, the flow to the field will be 100% of design. As the load in the field starts to reduce, control valves start to close and reduce the field flow and increase the pressure in the system. As the pressure increases, the bypass will start to open. When sizing the bypass valve, you need to make an assessment of the maximum flow through the bypass and the corresponding pressure drop of the bypass valve. Now, with variable flow chillers, this gets a bit more complicated, but for a simple system with a constant flow through the chiller, the maximum flow through the bypass is 100%. So if the field closes down, all the flow needs to go through the bypass. And the pressure drop, this is the other thing that people scratch their heads about. What will the pressure drop through the valve be? Well, looking at this diagram again, this bypass valve at 100% flow, just bear with me a moment, I'll give you a bit more in a minute, but if you've got 100% of the flow through the bypass, it's sending a message to the control system, to the chiller, that there's no load in the system. But to maintain stability, the pressure drop of that bypass valve has to be the pressure drop of the field. So downstream of the bypass and back to where the bypass joins back into the return, you can calculate that pressure loss in the field. That's the pressure drop through the bypass valve at 100% flow. That makes sense? It's pretty simple, really, in this case. So there'll be a very high pressure drop through the bypass, which means the bypass valve will be quite small relative to the pipework. Okay. So I've probably said most of that that's highlighted there. So that the bypass valve, let's say you've got a 100mm pipe, that's your pipe for the system. Your bypass might only be 50mm because it's got to provide a high pressure drop. All right, let's have a look at chiller control. So I say that when we get into more complex systems, which we're going to talk about a bit today, bypasses can get quite complex. I worked on a project a long time ago, a very big project. It was a resort, hotel, casino, convention centre. But that was in the days before we had variable speed drives, and before we had, it was just a constant flow system. We had 3 bypasses. The 3 bypasses were all different sizes, and they came into play at different points of the flow. There were 4 chillers initially. There's the same place now. It's got about 6 or 7, I think. But so 4 pumps, 4 chill water pumps, all pumping into a common system, and then 3 bypasses on the return. So it was pretty complex at the time, but these days you can have variable speed pumps, variable speed, variable flow chillers, and primary, secondary system, variable primary systems, and we'll talk about that a bit more shortly. So chiller control, there are various methods used to start and stop chillers, and you need to have some dialogue with the chiller suppliers in this regard as well. You can come up with your ideas, but make sure that you discuss it with them because really they're the experts. The chillers will only be required when the field is calling for cooling. There's no point running them if there's no load out there. If a zone temperature sensor in the field signals that cooling is required, the corresponding air handling unit or fan coil unit chill water valve will start to open. Now, again, what I'm about to say, there's various ways you can do this, but I've taken this information from Aera Design Guide DA28, which is Building Management Control Systems. It gives you various typical scenarios for control, for everything. So it's worth having a look at. Typically, a chiller cooling coil will be enabled when a control valve is more than 80% open for 5 minutes. So there's one zone cooling for cooling. You wait for 5 minutes to make sure that's a real coil before doing anything else. The time delay ensures that the cooling coil is sustained and prevents short cycling of the chiller. Minimisation of chiller cooling coils is a factor in energy efficient operation. So you don't want to be starting the chiller, turning it off, starting it, turning it off, and that will lead to failure of the chiller as well. If the chill water pump is not running, it'll now switch on and start to deliver water to the field. So you can start circulating water in the field, and then the chiller will then receive a signal that the pump is running satisfactorily. Either a differential pressure sensor in the chiller, quite often they come with a DP sensor. If they don't, you can put one in across the flow and return of the chiller, or you can have a flow switch in the chill water flow pipe. The flow switches can be unreliable, so differential pressure is preferred. Once the chiller starts, it'll operate under its own controls, usually to maintain the preset leaving chilled water temperature. So again, on this little diagram, I've showed a DP sensor across the inlet and outlet of the chiller. But as I said, quite often that is actually included in the chiller controls. There's a flow switch shown here as well, but preferably don't use them. They're unreliable and they fail. The chill water return temperature sensor will play a part in the loading of the chiller. For example, at full load in the field, with the chilled water leaving temperature, the supply temperature at 7 degrees, chill water return at 13. If the return water temperature decreases, so it's below 13, closer to the supply temperature, it's an indication that the field load is reducing. So the chiller controls will respond by reducing the cooling capacity of the chiller by whatever means, whether they start turning off compressors or slowing down the compressor, but still maintaining 7 degrees leaving temperature. That's the key, is the supply temperature to the field. That's what you always want to maintain. If you allow that to drift up, then you'll have problems with capacity control and humidity control. So if it gets up to 8 or 9 degrees, suddenly you'll have complaints about humidity because you're not dehumidifying. Again, this is from DA28. Typically, the cooling coil will be disabled when all the air handling unit valves are less than 30% open for 5 minutes. The control system has to monitor this. If you've got a BMS, if you've got this type of system, you'll have a DDC BMS system. So all this data can be looked at and decided when the chiller will shut down. So if the control system disables the chiller, it sends a signal to the chiller to say, we don't need you anymore. The chiller will shut down under its own control system safety devices. And if all the control valves close, well, the pump will stop as well. It doesn't need to run. So that was one chiller. If you have multiple chillers, it gets a bit more complicated. The control system will be more complex, but usually follows similar parameters. In this situation, it's necessary to develop a staging strategy to optimize chiller operation and efficiency. So you'll stage the chillers so that initially when your load is less than the load of one chiller, obviously you only need one chiller. If it increases past that, you need another chiller, and so on. So chillers stage up That's a terminology that's used. Staging up or more chillers are called for when the primary chill water supply temperature is more than 2 degrees above the set point for more than 10 minutes. Again, this is from DA28. You might have your own ideas on how to do this or talk to the manufacturers. But that's indicating if you can't maintain the leaving temperature from the chiller, it means the chiller can't produce enough capacity to achieve that. So you need to bring on another chiller. So there's that. And the current stage chiller electrical load is greater than 95%. So it's nearly at full load and it's not maintaining the chill water temperature. You need another chiller. And also, if any valve is more than 80% open for 5 minutes, well, obviously that's going to happen anyway. That's the first stage of turning the chiller on. Chillers stage down, or less chillers are called for when the current stage chiller's total electrical load is less than 85% of full load for the next stage down for more than 10 minutes. It's a bit of a mouthful, but really it's quite simple. For example, 2 chillers are running, but the total electrical load is less than 85% of the full load for only 1 chiller. So that means that 1 chiller can satisfy the load. So you can turn the second one off and let it run on 1. Now this scenario was based on non-VSD chillers. There are details for VSD chillers as well. And again, they're more complicated because you'll find that some VSD chillers, such as magnetic bearing chillers, actually have peak efficiency less than 100%. So you need to take that into account as well. So you might run 2 chillers at 50% rather than 1 at 100%, if that makes sense. You'll find that might be a more energy efficient operating point than running 1 at 100%. All right, so I'm going a bit fast, but you can review the notes anyway if you want to go back over it. I just wanted to talk about chill water system configurations because you're going to come across this if you haven't already. Various configurations are possible depending on the project type and size, and I'm just going to talk about the most common ones. So firstly, a fixed primary system. We've sort of been talking about that this morning. 1 or more chillers, constant flow, bypass valves to maintain the flow through the chillers, and 1 pump per chiller, 1 chill water pump per chiller. Chiller staging, normally controlled by a program lead lag arrangement. So your leading chiller, if it's the first chiller cooled on, will be a leading chiller. And then if you cool on another one, it's called a lag chiller. Now that arrangement can be rotated by your control system to ensure that you're getting similar wear on all the chillers. That's the basic system, but it's still relevant and still used, particularly with scroll chillers and smaller chillers like that. They'll just run on a constant flow. The bigger chillers, bigger centrifugals and screws may have variable flow. Now, primary secondary system. You may have heard of it. I'll just show you a diagram of it. So in a primary secondary system, you have a primary circuit. So you've got the chillers and the pumps and a bypass, buffer tank, back to the chiller. So that's the primary circuit. The secondary circuit is the field loop. There's more pumps with VSDs in this case, and they feed out to the air handling units and fan coil units, whatever's out in the field, and then come back to the main return line and back through the chillers again. This configuration, it's also called a decoupled system. It's commonly used in large applications where there's multiple chilled water circuits. So, for example, hospitals, universities, campuses, resorts, and so on. So you might have a number of buildings in the site. Each site has its own circuit. Each building has its own circuit from the in the secondary system. The system uses two separate loops, as I just said. The primary loop circulates chill water through the chillers only, via a bypass pipe. In this case, it's called a decoupler. The secondary loop circulates chill water through the field to air handling units and fan coil units and other cooling equipment. So this decoupler, the blue one, doesn't have a control valve in it. It normally has a magnetic flow meter, and the magnetic flow meter can measure the flow and actually the direction of flow. Because in the primary secondary system, it's very rare that you have a balance between primary and secondary. If all the water from the chillers is going out to the secondary circuit, then the system is completely balanced. It means you've got the load in the field exactly matches what the chiller is producing, but that's not happening all the time. It's kind of rare. So this is why you have variable speed secondary pumps. So the flow through the decoupler can go in either direction. Preferably, there'd be a small flow through the small positive flow from the primary circuit. But sometimes if the load is building up and your chillers haven't caught up to the load, you might get some recirculation through the decoupler in a negative direction back through the secondary circuit. So the water is going around here, not all of it, but a small amount might be coming this way, as the arrow shows there, back to the secondary pumps, and that's going to affect the chill water temperature because this water in the field is warmer than the supply. And your control system will then pick up. I don't want to go through the controls in detail because we'll be here all day, but it'll pick up that that's happening, that there's a flow in the negative direction and the temperature in the field is increasing. And then it says, well, we need more chill water capacity. So that's part of the staging strategy as well, that when that happens, you need more chill water. The concept is simple, but achieving it with the controls is not always as simple. Each loop has separate pumps, and the two loops are decoupled by a bypass pipe, as I've said. Traditionally, before VSDs came in, the primary pumps ensured a constant flow rate through the chillers, but there have been advances in chiller design, and the flow rate through the chillers might be variable. So that's another complication. The decoupler is common to both the primary and secondary loops, as I've said, and allows a small portion of chill water to flow either way to match the demands of the primary and secondary pumps. I'm just going back over what I briefly said. Ideally, the flow in both loops would be identical and there would be no flow in the decoupler, but this is rare. Practice, it's preferable to have a small positive flow in the primary direction to ensure that the field supply temperature remains at design value. So if you've got that small positive flow through the decoupler, it means that all the water going to the field is at design temperature. So if your design is 7, that's what you're getting out in the field, and that's what you want. But if you're getting more demand in the field and you're getting some recirculation, the temperature will go up, and that's not desirable for controlling the loads in the field. And that's when your chillers need to stage up. Secondary pumps circulate chill water from the primary loop to the cooling loads. These pumps are always variable speed to deliver the required amount of chilled water required. So you don't have a motorised bypass. The two-way valves in the field, when they close down, there's less water required, so the pumps will slow down, and eventually the system will acknowledge that and start to turn chillers off, or that's the most likely scenario. The primary secondary configuration provides better control and efficiency than a fixed primary system. As I said, this was the example I gave you before. Before all these systems were designed, before we used primary secondary in Australia, I did a very large project. There was a constant flow, 4 separate loops out in the field. There was a convention centre, casino, hotel, and another area. It was all fixed flow. and with 3 bypasses. So that was quite complex as well. The decoupling of the loops also helps to reduce pressure fluctuations, improves system stability, and simplifies maintenance and future expansion. So that's another thing. If you think that the project will grow, primary secondary is ideal because you can add more loops to your system, more secondary loops. One particular university in Queensland that I did a fair bit of work with, so it's a campus, multiple buildings. They might have 30, 40 more buildings on their campus. They had a primary system in the plant room, a secondary system outside the plant room, and then tertiary systems in the buildings. So the secondary system was delivering water through the reticulation around the campus, which was all underground pipework in a secondary system. Then the branches off to the building were a tertiary system. So that was a bit complicated again, but we won't go into that at the moment. Keep going. Variable primary systems. These are relatively new. A variable primary chill water system, also called primary flow or VPF, is a more recent alternative configuration. Now, the reason that these came about, because chillers now available with variable flow, variable speed, it wasn't necessary to have constant flow through the chillers, and therefore people started saying, well, do we need primary secondary? Can we just have variable primary? Which means you don't have the secondary pumps, you just have primary pumps. So I'll show you a diagram of that, which is same as the other one, but I crossed a few things out. So in this case, you don't have the secondary pumps. It's a variable primary system. So the pumps at the chillers pump the pipework, pump the water through the chillers and then out through the field and then back again. And in this case, there is a motorised bypass because you have to maintain that minimum flow through the chillers. Again, there's a buffer tank there. So talk a bit about this. As I said, there's only one set of pumps operating on variable flow control to optimise the energy efficiency and system performance. So people thought, well, okay, let's take advantage of the energy efficiency opportunities with the chillers and VSDs on pumps. The chill water, in this case, flows directly from the chillers to the loads without a secondary loop. Speed of the pumps is modulated based on the cooling load in the field, and also the bypass is controlled. So that this is quite a complex control system. By varying the chill water flow rate based on the cooling load, the VPF system can optimise energy consumption. As the cooling load reduces, the pump speed reduces, chiller capacity reduces, and that provides big savings in energy consumption. When you look at chiller power requirements, they consume a lot of energy. So anything you can do to reduce the energy consumption of a chiller is going to make a big difference to the energy consumption of the whole system. The chiller is the biggest user of electricity in your project by a long way. So if you can reduce the energy of the chiller and the pumps, then you're getting some good savings. Not only in energy efficiency, but also in cost. So you've got less plant involved. Instead of having the secondary pumps, valves and controls, you don't have them. You've got primary pumps only. The control system does get a bit more complicated, but the actual equipment involved is less, and there's some savings there. So I've said both the variable primary and primary secondary require a bypass. In the primary secondary, the bypass is actually just a decoupler with a flow meter, but you need the motorised bypass valve for the variable primary. The bypass pipe in the variable primary will be smaller than the fixed primary as the flow rate is lower to match the minimum flow through the chiller. So minimum flow through the chiller is the key, okay? In a fixed system and the smaller systems, you'll have to maintain 100% flow through the chiller. But in a variable primary, if you've got a variable flow through the chiller, your bypass can be smaller because the minimum flow will be a lot less. Decoupler in primary secondary is an open header and usually includes the magnetic flow meter to indicate the direction of flow rate. Now, I was involved in a project which we didn't design. It was designed by somebody else. Just going back a while now, in the earlier days of primary secondary, and this particular designer wanted to make sure that you could never get a reverse flow in the decoupler. Okay, so it's not recirculating through the secondary side. They didn't want that to happen. That's a fundamental part of the primary secondary system, but they didn't want it to happen. So they put a check valve in the decoupler to make sure the flow could only go in one direction. But don't do that. That doesn't work. So what we ended up doing was we put they insisted that we had to put it in. So we put it in and we took the insides of it out. So it was just a pipe. And we didn't tell them. But anyway, but it worked because it didn't work with a bypass. It didn't work with a check valve in the bypass. Don't do that. The usual way is just with a magnetic flow meter in. It'll tell the controls which way the flow is going and then lead to staging of the chillers or upstage, downstage, whatever's needed. Now, in a primary secondary system, the primary pumps obviously have to handle the total system flow, but only to pump it through that primary loop. So the pressure drop for the primary pumps is relatively low, but the secondary pumps handle the flow and the pressure in the field. So you've got two sets of pumps doing the same total flow, but with different pressure. But in the variable primary system, the primary pumps are the only pumps and have to handle the pressure of the whole system. So be aware of that. And I'll put down a few advantages of the variable primary. It has a lower installed cost compared with primary secondary because you don't require secondary pumps, VSDs and valves, etc. There's a lower chill water pumping energy due to variable flow through the chillers. Less plant space required because you've got less pumps and other pipe work. And higher reliability only because of the fact that you've got less pumps involved. Some of the disadvantages, and look, they are complicated. We have done them, and you just need to make sure that you're talking to the chiller suppliers, the control suppliers, you all work together to make sure that you achieve all of the things you need to do to make it work. More complex control system, commissioning is more complex and will probably take longer to set it up. Bypass control is more complex. You need greater sophistication from your operators. So your operators really need to be trained on how it works. And I have been involved with a project where the operators hadn't been trained. They didn't understand it and they complained about it. But once they understood how it was supposed to work and how to keep it running properly, they were quite happy with it. The EPF is not recommended for applications where chill water supply temperature is critical. So you might get some fluctuations in the chill water temperature. If you're doing a clean room or laboratory, maybe that's not acceptable. So you're probably better off with primary, secondary. And if you've got all three-way valves in the field, there's no point having variable primary because your flow is going to be constant. So I've just summarised there. VPF is more complex than a primary secondary, but does have potential capital and operating cost savings. So it's interesting to do one, and you'd need to justify the difference, the value in doing it. Okay, we've reached 11 o'clock, but I'll just finish off. I just wanted to mention chillers in series, in a series counterflow arrangement. And normally, the chiller, well, if we go back to the primary, secondary, or the variable primary, the chillers are in parallel with the circuit. Okay, that's a parallel arrangement. The chillers are in parallel. Variable primary, the chillers are in parallel. However, in a, I'll show you a picture of a. So this is a series counterflow. In this case, the chillers are installed in series. So the chilled water flows through one chiller and then through the other one. So in the first chiller, it might go from, say, 13 to 10. In the second chiller, 10 to 7. And the cooling tower, the condenser water circuit is counterflow, so it goes in the other direction. Now this, so in the example that I've shown there, the reason that the benefit from, oh, sorry, I just messed that up. Because the higher chill water leaving temperature of the first chiller, 10 degrees, the chiller efficiency is considerably higher than the second chiller. So I've mentioned this in previous sessions, but it's coming out of the first chiller, in this case, at 10 degrees. And then from the second chiller, it's getting down to 7, which is the design for the field. The higher the leaving water from the evaporator of a chiller, the greater the efficiency of the chiller. Okay, so if you've got one chiller that's producing 7 degrees, it's going to consume more energy than if you have two in series, one that's coming down to 10 and one that's coming down to 7, because the efficiency of chiller 1 will be much higher. Chill water, as I said, chill water entering and leaving conditions can be selected during design to maximise efficiency or to minimise the cost or may be required for humidity control. It's common these days to have a greater range in the chill water temperatures. A lot of projects that I was involved with in recent years had a chill water temperature range of 15 degrees to 6 degrees. Even higher, even 16 to 6. The relatively large temperature differential means that chill water flow rate is reduced. Okay, so you've got a bigger temperature difference, lower flow. And that has advantages in your pipe work, in your pumps. So you can have smaller pumps and pipe work, but make sure that the cooling coils are selected to operate on that design temperature range. If you do a refit, a retrofit on a project that was designed, say, 10 years ago, or whenever it was designed, you need to check what the cooling coils were based on. If they were based on a temperature difference from 13 to 7 degrees, or entering at 7, leaving at 13, and you change the system for 6 to 16, you're going to have problems with the system because the coils aren't designed for it. So with a larger temperature difference, your pumps and pipes are smaller, but the coils may be bigger because you may need a bigger heat transfer area to get the same effect. So just be aware of that. There may be some additional cost in the coils. As I said, in the scenario that I showed you, if a parallel chiller arrangement is used, the chiller efficiency will be reduced due to the low leaving chill water temperature. If they're in parallel, they're both producing 7-degree water, the efficiency will be lower than if they're in series, and one's producing a higher chill water temperature, which is then reduced by the second one. I hope that makes sense. But if you look at chiller efficiencies, change the leaving temperature, you will see that the efficiency goes up as the leaving water increases. However, the field is still going to require, say, 6 degrees or 7 degrees water for the system to work properly. So you need to have them in series. This is not common, but it is a good energy efficiency thing to look at if you're assessing different types of systems. And be aware that in the series arrangement, the chilled water and condensed water pumps have to handle the higher system pressure, have to handle a higher system pressure drop, because they have to overcome the pressure drop of 2 chillers in series. So a typical pressure drop through a chiller might be, say, 30 kPa. And in the parallel arrangement, that is the pressure drop you take into your calculation. But if you've got them in series, you'll have 2 times 30. So it'll be 60 in that case. So once again, we've skimmed through that pretty quickly, but I just wanted to give you some awareness of the different systems available. And you're going to hear these terms. People will talk about it. So that's what they are. There's an unlimited amount of information available online to read up about it. Train in particular have a lot of good technical information available online. So, if you want to read some more. Later on in this training series, I'm thinking that we might talk more about selection of chillers. So do some examples. Certain loads, what sort of chiller would you select and why? And that'll give you a bit more information about how to go about it. Obviously, there's a huge range of chillers available, a huge range of capacities depending on the project. So it's a matter of choosing the best one for the project with all things considered. Next week, we're going to talk about boilers in a similar vein to today's discussion about system arrangements and control. Now, that won't be next week. That'll be when I come back. I'm going to be away for 6 weeks. So that'll be at the start of September, I think, the next one. I sent out the agenda. I think it's the 5th of September, but you can check on the agenda I sent out. Thanks to boilers, we're going to talk about cooling towers and some of the important things to be aware of there, and fluid coolers. But in particular, cooling towers, because they're a more challenging animal and have certain fundamental things that you need to be aware of and make sure you are implemented when you're designing one of those systems. So we're going to try and get a bit more, dig a bit deeper again into the actual installation requirements and operating requirements and selection of this equipment as we go along. So I'll see you again at the end of September. Any questions before we go? Sorry, I'm losing my voice. Any questions?
I just had one question with the series arrangement for the chillers. How does the spatial requirements compare when you have 2 chillers in series opposed to having one that might have the same capacity?
Yeah, that's a good question. The staging of them. Well, to be honest, it is complex. And again, you need to be talking to the chiller suppliers to see how they want to do it. Now, I haven't mentioned this, but it's quite common these days, particularly where you have that sort of arrangement. Primary, secondary is pretty straightforward. Variable primary is getting more complex, and series counterflow is complex as well. So what is normally done is the chiller suppliers will provide the package for the control of the central plant. So the decision would usually be with them. I mean, designers will have their ideas, but you really need to talk to the suppliers to see how they want to operate the plant. And so the likes of, most chiller suppliers these days can provide a central plant control system. Okay, so you want to get one of those so they control the staging, the water flows, the pumps, everything. So I haven't answered your question, but you need to talk to the suppliers about how they would want to control that.
What about the spatial requirements? Like, because in your diagram you had
Oh,
two.
did you say? I thought you said staging. Did you say spatial?
Yes, I did say spatial. Sorry.
Oh, sorry.
Like in
Sorry,
your
Stephen.
diagram.
I thought you said staging, which is quite complex. But spatially,
Yeah.
So are they? Well, they can either be in line with each other, so one after the other, and you can have your pipe work going through one and then straight through the next one, or you can, you can take the pipe work around. You can have them sitting side by side. It's just a matter of getting the flow of the pipe or flow of the water in a series arrangement. So they can still be side by side, but you've got to make sure that the water coming out of one goes into the other one and then out the other end. So yeah, it just depends on the, I suppose, the architectural provisions in the building, whatever works best. I guess the thing that would work best if you can dictate the space that you want is to have them in a line to keep the pipework straight. So straight out of one and straight into the other, rather than go through a series of bends back into the other one, which is going to cause extra pressure drop in your system. It doesn't really matter as long as you get the configuration correct, that the flow is in the right direction and the condenser water is going in the other direction to get the maximum efficiency. But yeah, just on staging, that is quite complex. And I think it's best if with these large central plant systems, if you do use the manufacturer's central control system. So they control the chillers and the pumps and the cooling towers, everything associated with that plant. And then your BMS next to that picks up all those points so it can monitor. It doesn't provide control, it'll provide inputs to that control system, but it doesn't control the system. The system's controlled by the chiller, the proprietary chiller control system. It's probably the safest way to go.
Yep, thanks.
Anything else? Okay, well, thanks for attending, and we'll see you when I come back.